The last team I'm going to hear today is team number 15, BNS Solutions. The customer is BNS Solutions. The customer is here, and whenever you're ready, guys.
Good afternoon, everyone. We are BNS Solutions, and this is Heng, this is Jung, and this is Randy Lee, and I am Kimaya Agarwal. Before we begin talking about our project, we would like to set the stage by giving you an overview about brushless DC motors. While using DC motors, designers tend to use brushless DC motors as they are less susceptible to wear and tear as compared to brushed DC motors. And they have a wide range of applications such as solar tracking systems, robot arms, and water pumps. When these motors work efficiently, they become very cost effective, they help us save fuel, and they also have a lot of clean energy applications. Therefore, it is very essential that these systems are working efficiently. Now, I'll give you some information about how motor developers could make sure that the motors are working efficiently. So here we have a motor control system that controls a 3-phase simple brushless DC motor. And to this motor is attached a rotor, and to the rotor you can see is attached a magnetic disc, and it has 4 magnetic poles. And then T, S, and R, the labels, they are the Hall effect sensors that are attached to these rotors. And every time the north-south boundary of these rotors crosses over a Hall effect sensor, the output of the Hall effect sensor changes from 0 to 1 or 1 to 0 respectively. And this creates a commutation zone. And this information can then be used by motor developers to understand what position the rotor is angled at. And this would help them maximize the torque that the motor gives out. We also have the phase and current diagram for a simple brushless DC motor, and superimposed are the commutation zones that you can see here. There are a lot of systems that can analyze these motors, and motor developers could just cross their fingers and hope and pray that the control system is working fine. Or they could use these systems that analyze it. But most of these systems are not integrated, and it is very hard for motor developers to understand what's going on because a lot of inputs have to be taken into consideration. That's where our platform, MocoDAPS, comes into play. The main objective of our platform is to build an integrated data acquisition platform for motor drive analysis that would help motor developers make their motors more efficient. So our platform would collect analog and digital signals from the motor, transmit this information to the PC, and all this data would then be graphed live on our software. To give you a better sense of what's going on, we have a visualization here, and on the top you can see we have a motor driver and a motor. Our project is to not work on the motor driver or the motor, but to build a platform that works with it. So on the bottom you can see we have the PCB and the enclosure that we used, and the motor would send in analog signals and digital signals to this PCB, and then this information is sent to our RL78 microcontroller, and then packages this information and further sends it to the virtual COM port, which we have. And then via a USB port, it is sent to our PC software where everything is graphed live. For simplicity, we broke down our module into 3 sub-modules. And on the left, we have the data acquisition hardware. On the top right, we have the communication firmware. And at the bottom, we have the graphing software. Now I'll let Steve take over the stage and talk about the data acquisition hardware.
So, as we begin to talk about the functionalities of our system, it's important to understand what kind of inputs we're going to be dealing with. A request of our customer, there should be a minimum of 3 differential analog channels, 2 single-ended analog channels, and 8 digital channels. Taking in the 8 digital channels is the easiest to implement and to pass 2 GPIO pins on the MCU, as all that's needed is a clamping circuit to prevent any inputs from exceeding the PCC of the MCU, which in our case is 5 volts. The analog channel is a little bit more involved, as more operations is necessary to condition them. The signals themselves can range between 0 to 45 volts. However, as a design choice, which I'll explain a little bit later, the circuit can handle signals between negative 45 to 45 volts. The circuit bandwidth is 0 DC to 53 kilohertz, which is slightly larger than what was requested by our customer, mainly because we wanted to sample all the signals at the correct frequency without any cutoff and without any attenuation. External probes will be used without circuit. Therefore, the internal input capacitance and the input impedance should be known. Therefore, the input capacitance per channel is 13 picofarads, whereas the input impedance is 3.3 megohms. So the operations for our circuit will implement a buffering module, attenuation, filtering. It should digitize all analog channels, as well as transmit every signal over to the computer via USB, including the digital channels. While designing the circuit, we kept the user in mind. We wanted to create a system that would be easy for the user to use without having to implement too many steps or any procedures that would kill the performance of our circuit. We wanted to protect any damage or any user error against the or any damage towards the user, towards the circuit. The way we implemented this was by using over voltage protection, reverse polarity, ESD protection, and in the event that the user swaps or sets up the circuit without configuring the system, the circuit will be safe and will not be damaged. So from a design point of view, the first thing that was implemented was a simulation of a conceptual circuit that would implement what kind of circuit we want to create. Shown on the left is a single differential analog channel, and what was resulted from this was a promising result that we can actually create a mock circuit from show that the circuit would work. And during the testing day, we created this mock circuit. The operations were not at par, mainly because the components used were not what we needed. They were just components laying around the lab. Therefore, a prototype PCB was made using the components that would be used in the finalized design. So here's a schematic of the finalized design for a single differential analog channel. On the first module, which is shown on the far left over here, this whole module over there is the attenuation module. This is mainly there to prevent any signals, since the signals can range between 0 to 45 volts. We wanted to make sure that the MCU or the ECE would not be damaged. Therefore, an attenuation of 10x, 7x, or 3x, depending on what kind of signals is passed to the MCU, will be attenuated accordingly. This is implemented by using switching network resistors that regulate what the voltage divider will be, with the use of an OR gate, fuse switches, and a logic level MOSFETs. All 5 analog channels can be attenuated accordingly. Here's the MCU with logic level level shifters surrounding the MCU, mainly to assure that proper communication between the ADC and the FTDI chip will be implemented correctly. So here's the FTDI chip with the double EEPROM on the top right, and on the bottom the USB connector. As you can see, there's extensive filtering. This is mainly because we're powering the board by USB. Since this USB power is very noisy, we want to prevent any high frequency noise from entering the system. Therefore, ferrite beads and TDS diodes were implemented, which will reduce all high frequency noise and any voltage spikes that will enter the circuit. On the bottom, there is a current limiting module that will limit the circuit from pulling in greater than 500 milliamps from the computer. And the last of the schematics is just the miscellaneous circuitry. On the top left is the OR gate. On the right hand side is the 5-volt inverter. Bottom is the digital inputs and the debugging header. We created a 2-layer PCB board and the circuit. Here's the PCB circuit itself with the enclosure surrounding it. And finally, some circuit performance and how well the signals are conditioned. On the top, you can see the input signals, which is the PWM modulated signal, which can range between 0 to 24 volts at a frequency of 20 kilohertz. On the bottom is the output signals that go right prior to the EDC. As you can tell, the signals are conditioned and are attenuated accordingly. Therefore, the ECE will read signals without any damage done to the circuit. For a closer view, here's the same signal, but just at a 15 microsecond time deviation. The top represents the output curve, the bottom represents the input signals.
So for the firmware module, the firmware is primarily responsible for initializing hardware, firing the data, packaging this data, and then sending this data over to the PC software. So the first primary point is the initialization of the hardware. This is done from initialization instructions sent over from the PC software initially. This sets the attenuation for the analog channels, which can be either a factor of 10, 7, or 3, the number of analog channels that will be used out of the 5, and also whether the digital inputs will be used in a particular acquisition session. The second point for the firmware is establishing a communication protocol between the PC software and the controller so that data can be sent over, the proper initializations can set the controller and hardware, and also send data over as well. So, in addition, another issue that came up was increasing data transmission rates, and this was achieved by reducing the ADC the bit resolution we had from 13 bits to 8 bits, just to downsize the number of bytes we had to send over for one sample packet, and also making the analog channel range and digital channel range adjustable according to the user specifications, as well as some other transactions. So this is a general flowchart of the firmware. First, system powers on and initializes your communication between the PC and the controller. And then the user sends initialization, that is attenuation, the number of analog channels that will be used for their digital channels will be used over to the controller. Next, once a acquisition session is started, the ADC will acquire data, this ADC, and then next the digital data will be acquired if this was required by the user. And then all this data will be packaged and sent over to the PC. And this will continue to loop unless the user ends or pauses an acquisition session where he or she can change the attenuation or the channels that we use. So here's a simple outline for the communication protocol. Primarily, you just need to initialize the hardware, that is setting the attenuation, 2 bytes, and then the number of channels that's coded in the second byte, and the digital input is also just added into a 4th byte. And that doesn't really affect the transmission input. And then once again, there's a transmission byte. There are transmission bytes, 1 for each channel that's sent over. So this is dynamic based on how many channels are chosen by the users, which is potentially 6, and then there's a stop.
Hello, my name is Ben. I spent most of my time writing the software. So this right here is the block diagram of our software. It's a PC-based software written in C#. Seen here is the submodule, and it's split up into more submodules that we can work on separately. Lately, we've been working on the DSP and analysis modules based on our knowledge of ideal motor timings. The conceptual aspect has been completed, but we weren't able to integrate it into our working oscilloscope software as of now. However, we have gotten all the other submodules completed. Okay, so when you first start the application, this is going to be the first form that greets you. It's the main motivation for this form was to make setting up the program easy for users. One of the problems I always had was whenever I started the program, I'd always have to figure out what COM port the USB was connected to. So I wrote a little script that essentially populates the COM port right over here. So this gets populated automatically, so you know what's connected and what's available. And I also made it easier so you can load the default settings. These default settings are basically what we decide is most compatible with our hardware. You can also enable or disable the hardware. The reason why I did that was because I tested most of the software on, I couldn't test it on the unfinished hardware, so I tested it with a loopback FTDI chip. All these settings are persistent and they're saved in the software. They're accessible by the main form as well. And I also made it an option in case users would like to transport their settings to another computer to export or import their settings. Okay, so once the settings have been applied, the main form will appear, and the main motivation for this was to mimic the functions of an analog oscilloscope. As you can see, this is basically a multi-input digital oscilloscope. There are vertical controls over here. There's a trigger, horizontal controls, and there's storage options. You can save the data as a CSV file, an image of the graph, or you can print the graph as well. Some of the design choices behind the software was how to control the data, and instead of using a data set, I decided to use multiple ring buffers. In order to optimize graphing, especially for managed code, I decided to scale it because it's kind of pointless to plot, let's say, like 50,000 points in a screen resolution of less than 2K. I also used a lot of pointers just to keep track of where the pointer is whenever it's acquiring data, so that users will always have at most a full second's worth of data. The pointers were also used in order to help with the delay functions, which you'll see shortly. So here's an example of a single channel graphing of a 5 kilohertz 25 volt peak-to-peak sine wave. Shown here is an example of the oscilloscope features, all the features being implemented. So you have the voltage division, the positioning. So I kind of just, it was a 0 to 25, so I kind of moved it down a little. There's also a trigger. I set it on falling edge. There's a falling edge, rising edge, and level trigger, just like on analog oscilloscopes. I set the level to be -4, so you can see that with this red line right over here. The delay is set at 8 units. This unit is just based on the graph. It's not based on the actual values. And as you can see, right over here at this point, it's fairly accurate, even though this is a discretized value. And here is an example of the software graphing multiple analog inputs. The values are actually the same, but in order for them to not be overlapped, I changed the voltage divisions. So you can kind of see it like ramping up at different rates. And this is the flow of the software. Each box represents an event. All the arrows are conditional unless they're unmarked, in which case they're unconditional. Users start from the settings form, and once they click OK or cancel, they go into the graph configuration optimization, and then they usually end up in one of two places: either wait for user input, or if they select various conditions, they end up in the loop, and this is where the graphing takes place. Data acquisition and updating the graph data is actually in 2 separate threads that happen concurrently, just so we can keep up with the data input. You'll notice some of these arrows are actually colored, if you can see the colors. And this is just to indicate the flow of events if specific conditions are met. So for one example, in the, while it's in the loop, since it's running in separate threads, you can, the user interface is still available for use. So if you happen to change the time division, then it'll go into this event where the horizontal scaling or delay is activated, and unconditionally go to stop data acquisition, and then configure the graph and optimize, and then restart the data acquisition process, in which it'll end up back in this loop. So, as Kim mentioned earlier, one of the problems with making efficient motors is that there's not enough. there's not a platform in order for motor developers to actually use. You can make one up by integrating separate parts, separate pieces, but that ends up being a lot more costly and it takes up a lot of space. So with our system, you can actually, it's actually an integrated and compact platform that acquires all the data that any motor developer would need. So these would be for the phases, these would be for the analog inputs, and then these are for the Hall effect sensors, and simultaneously graph it on our software. Yes.
If I were a motor developer and without your system, I were to buy pieces to do what your system is doing, what am I talking cost-wise versus what your system is?
So the cost for our circuit or the system itself will be around $150 to $160.
And this would be cheaper than?
Oh, well, if you have, like, for example, multiple oscilloscopes tied in together, maybe just syncing them up together, that's definitely going to be a lot cheaper than buying multiple oscilloscopes and doing what we want to do. This package, this integrated system is fractions or cheaper than doing that. So let's see.
I'm just seeing a link. Clearly have developed a very fine data acquisition system. In the beginning it talked about motors, turning. How are they related? What are you looking at on the motor and going to display on your data acquisition system? And how does that relate to the operation of the motor? Can you give us any information about that?
So the graphing portion of our software will essentially just overlay the graphs, and you can manually look at the values and kind of based on knowledge of how ideal three-phase motors should operate, you can kind of get an idea of what an ideal timing is. But the part of our software, sorry, I just have to look for this page. So the part of our software where we do the analysis, we would use our knowledge of ideal motors, and essentially, well, this right here is an ideal motor. So what we basically do is we take all the data and we compile it and analyze it and look for points where the motors begin to commutate, and that's when these switch polarities. What we want to measure is we want to measure where that happens specifically, and that's where the Hall effect sensor comes in, versus what we actually read from the analog signals, which is what's driving the motor. So, for example, if you look at this graph right here, when a motor is going from high to low, you want to make sure it commutates at this ideal point right in the center, as opposed to being earlier or later. Otherwise, the output would be not as efficient.
What are those dotted lines represent?
These right here.
Yeah. Early, ideal, and late with respect to what?
With respect to when the phases actually change.
So just to maybe help clarify a little bit, another way we can look at this is when we look at the phases of the three phases that's driving the motor. So if we look at, for example, signals phase, let's say one in, say phases A and B. You can see that A and B will be on while the phase C will be floating. At the same while the signals are separating by 120 degrees, the next pair will turn on and the other one will be turned off while floating. So the reason why there's a ramp The ramp over here is mainly because the inductor is just discharging its energy. By the time it reaches the off point, that's the moment in the commutation point. So if you look at all the points where they level out, you can see that that's where they commutate. If the commutation points are equally spaced, then you can say that the motor is rotating at a constant RPM, constant speed. If the motor is not running at a constant speed, then you can say that the motor is clearly not efficient. It's not running efficiently.
I think maybe I just missed this, but what operations can you perform on your inputs? Like, can you take the difference of two signals or add things, or like on those sort of match signals, frequencies?
That would be part of the analysis portion. Okay. We haven't been able to successfully do that.
We do have, in the demo we'll demonstrate that we do have DSP analysis on the signals themselves. So what we have right now is actually just a scoping aspect of our project. The next aspect of the project that needs to be completed is the analysis. The reason why we weren't able to complete it was because the scoping is essential before we actually do any analysis. We do have DSP, so I guess one thing to just look at very quickly is how the signals actually look like. Most of them are PWM. But in order to get maybe like an ideal, like the case that we just saw, we want to have a straight line and a trapezoidal shape. We were able to get a very similar signal to that, but we had like an overshoot, which is mainly related to the PID controller that's within motor controller. But if we were able to get the DSP to operate correctly, then we can analyze integrating the signals themselves and look into flux.
Yeah, that's what I was kind of thinking. Is since most of that's on the software end, it seems like if the user knows exactly what he wants to see on this motor, you could write the function for that, or just be checking for some very specific.
Yeah, like in addition, like for example, with this signal, what we are able to do right now with some kind of like detached software not integrated in the system yet, is just kind of like trace the density, so you can kind of see like in this example, the voltage in the PWM is mostly focused on the bottom part. It comes down and we go to the bottom. So that's primarily like the trend we want to take from these PWM signals. So we kind of use something like moving average right now, so we can kind of like track down the general trend like where the signal is most densely populated, or the voltage mostly is.
The analysis will actually be separate from the graphing in that it doesn't graph while it's analyzing, just because you want to take a screenshot of the data that you want, and then click a button for whatever type of analysis that you do. And it should be able to produce graph speeds based on that. And the reason for that is because the amount of data coming in and the amount of data that you have to analyze is just so large that it would not be efficient to actually analyze it live.
Is shaft dynamometer required? Would that not be part of what you would need for diagnosis?
I'm sorry?
Motor shaft dynamometer?
From our customer, that wasn't specified, and it was a requirement.
All right, thank you.